But before we deallocate it, we also take a look at the return info cell so that we know what else we have to do after we have ended the subroutine. We have to go back to line 8, but this time line 8 looks like this: return 1 plus 1. Are we ready to execute the return part of that line? There are no invocations left to do. The addition, we know how to do it already. 1 plus 1 equals to 2. In other words, at this point, which is row 29 of the trace, line 8 effectively becomes return 2. Okay? Because the first invocation returns a value of 1. The second invocation of f also returns a value of 1. Now that we know it is 1 plus 1, we can calculate it is 2, and as a result, line 8 effectively becomes return 2. Okay? But we are executing return 2 in the context of column C and column D, which means when we execute return 2, we use column C to supply the return info cell. We copy and paste that, replace the question mark with 2 because we are returning a value of 2, and we are done with line 8. After line 8, we get out of the conditional statement. We end up on line 10. And once again, line 10 is the end of a subroutine. We just deallocate the 2 columns that we allocated earlier for this invocation. And then we go back to the line that our return info is telling us to go back to. Return info, or column C, is telling me that I have to go back to line 11. Okay, so we go back to line 11. But line 11 is no longer looking like this because the invocation is now done. In fact, we know that the invocation is giving me a value of 2. Are we ready to print? Okay. When we are ready to print, we just have to go to the comments column and say that we are printing a value of 2. I don't really care whether it's appearing on the screen or a piece of paper. I'm just printing it out to some place. And after line 11, there's nothing else, and we are done with this trace. So this is a little bit lengthy and also kind of confusing, but that makes it a very good example because if you can work this out, that means you understand the concept of returning a value. If you're having a problem, like, okay, there's one place you're not quite understanding why we are specifying, a 1, a 0, or 2 to replace the question mark, that means you have to kind of, spend some more time to understand the mechanism of returning a value. Because the entire program is using a single mechanism to return values. We have not changed the mechanisms at all since the day that we talk about returning a value. It's just that in this case, it's a good test to see whether you can follow the mechanism by hand. Yep.
My only question is if in column G you deallocated the line on at one time,
right?
Why wouldn't the second line, if it's deallocated, why are we still going to use that column? Shouldn't that have been broken into 2 separate columns or something?
Can you refer to the row number so we can just look at a slice of time?
15.
Okay, row 15.
Yeah, row
okay.
15, column G.
Mm-hmm.
You've got the X's there, so you deallocated that column, but you're still using that column underneath.
Once you deallocate a column, that means it's available again.
Okay.
Look at deallocation as a recycle bin. If you put a piece of paper back into the recycle bin, that piece of paper can be used again. Okay, we are basically reusing the same piece of paper and overwrite it with new information. Okay. That's a good question. Any other questions at this point? No? This is all good? Okay, let me just get rid of these split lines here and decrease the font size just so that you guys can see the overall shape of this trace. You can see that it goes out like this, it kind of goes back, and then there's a little bit more, and it goes back, and that's it. Okay, so it's kind of important to realize what is the shape of the trace. In other words, when we are tracing programs, whether it's recursive or not doesn't really matter. You should see the allocation to go like this. It retracts, goes out again, possibly retract, and then go out again. In other words, it should be contiguous. it should not be something like this, okay? All the way, and then we start to allocate over here. That should not be the case. It also should not be something that looks like this. Goes all the way out, and then at the end of the entire program, it suddenly drops all the way back in. That should not happen either, okay? Are we doing okay so far? Okay, here comes a question that some of you may have in your mind, but just don't want to ask it because you want to be polite. Why am I being so picky about all these things? Why are we following these specific rules in terms of tracing? It seems like there has to be a more intuitive way of just do this, or whatever you do, if you give me the right result, that's fine. How come I'm being so picky about these rules and also the representation when we run the program? Go ahead.
Are you trying to match a particular program or C and how it runs?
Exactly.
And your logic needs to match that, otherwise the logic won't work in the programming.
Exactly. We are trying to mimic the mechanism of actually how a real program does it. Now, we are not just talking about C and C++, because in that case it would be a very language-specific concept. We are talking about just about any practical modern programming language. Okay, so we are talking about Python, we're talking about Perl, we're talking about C, C++, we're talking about Java, we're talking about PHP, and so on. In other words, all programming languages internally will represent stuff like this. Now, it doesn't really have return info. I mean, this is something that I actually have to come up, in order to represent how return values are treated. But basically, it has quote-unquote a placeholder as well, and there's also a way so that we can go back on the same line and find out what else on that line has to be done. Okay, it's just not kind of spelled out like this in text. It has other ways of specifying exactly the same thing. Okay, so that is why I'm being so picky when it comes to the mechanism of tracing, when the syntax itself doesn't have to be very specific. In other words, you can see that this time I use else if as one single word, and most of the time I spell out else and then a space and then an if. If any one of you want to use an abbreviation like ELIF, else if, or ELSIF, even without the E, that's perfectly fine with me, because that part is not as important. What is important is whether the mechanism itself is followed. Any questions at this point about returning values? Do you guys like recursion? No? Sort of?
What's the point of it? How's that? I understand its purpose, I understand the point of it. That doesn't mean it's fun to trace.
It is not fun to trace, but it does help to, if anything, recursion helps to expose, any misunderstanding of the mechanisms. And that's why I pick recursion in this, even in a class like this. Because it's better to expose a misunderstanding of a concept early than to expose the misunderstanding later. Because if someone has a misunderstanding of how subroutines are done, and only discover that understanding is incorrect by the time that person gets to CISP 430, it becomes really difficult to change, because you have been that person would have been using that same wrong concept all along, and it's difficult to change something when it has been used for several semesters already. So are we doing okay so far with returning values? Okay, if that's okay, we'll go ahead and work on another example. You can see that in the classes we just work on one example after another, because that's the way to really make you guys exercise and understand the concept from different perspectives. This time, let's combine something that we have not combined before, because a lot of concepts in programming can be combined without any problems. So let me turn on the formatting. I need that one. Yep. How many people still remember arrays? Okay. How about binary search. Okay, let's talk about binary search, but in the context of subroutines, return values, pass by reference, and recursion. Okay, so we are kind of mixing all those concepts together. Okay, because they all mix well. I mean, these concepts, they all mix well. So in this case, we'll just call this binary search, B search. It will take several parameters. Okay, it will take by reference A, which is an array. It will take by value parameter B. It will take by value parameter E, and it will take by value parameter K. So these parameters are going to be passed by values except for A, which is passed by reference. And the code of binary search in a recursive way is almost the same. It follows the same logic as what we usually have. In other words, we have a local variable m, to serve as the index of the element that we're going to look at. And the way we calculate m is exactly the same as before. It is the floor of b plus e divided by 2. Okay, so that part has not changed. We still have a conditional statement checking for several conditions. Now you can see that I don't have a loop anymore. There's no repeat until anymore. So in this case, we have the 3 conditions that we need to check for. The first thing is, well, let's see if b is already greater than e. Because if b is greater than e, I will return false. In other words, I know that the value k is not in the array A anywhere. Okay? Otherwise, I check for something else. Let's check for the easy one first. Let's look at element m of array A and see if that's what we're looking for. Because if by chance that's exactly what I'm looking for, I can just return true. Okay, the search algorithm returning true means that I have found it. Okay, I have found the element with a value of k. Otherwise, we will check for the other 2 comparisons. In other words, we check to see if a bracket m is less than k. In that case, we'll do something. Okay, in the other case, we'll do something else, and that's my entire conditional statement. And the funny thing is, I really only need a conditional statement. Okay, so let me go ahead and change the indentation a little bit to make it easier to read. I may not, even want to trace this one because it will take up a lot of columns. And, well, maybe it's not too bad because each column is only a letter, so maybe it's not too bad. I'm just going to do all the indentations first and then go back and backfill the code itself. Okay, now we are on line 13 of this algorithm. Can anyone tell me what I'm supposed to do? Am I going to adjust B or am I going to adjust E when a bracket m is less than k, assuming the array is sorted in a non-decreasing way? We adjusted B, exactly, okay? So, but in this case, we are not going to change B itself. In other words, we are going to invoke B search again, except parameter B is the one that gets changed when we pass it along. So here is what we're going to do. We're going to return something. We're going to return the return value of invoking binary search again. It's going to look really boring. We're passing A to A. We are doing something with B, so I will tell you guys what we're going to do with B next. I'll just talk about all the boring part first. E goes to E, and K goes to K.
Why is K going to E?
Oh, yeah, because it's a typo.
Sorry, I thought I got confused.
No, that's okay. Thank you. Okay, so the big question is, what is going to be? But some of you already answered the question earlier. We have to adjust B. Now, in the normal sense of a binary search algorithm, how do we adjust B when a bracket m is less than